Okay, hi. Uh, I feel very privileged to have been here today and sat through what I've sat through, not because of my own enjoyment. I think Stan would have really enjoyed sitting through the talks that we've heard today. So I want to start with that. Mine's going to be a little bit different. Stan never did work in gravitational waves, but I have a long history with Stan. So talking to Giorgio when he asked me to come, we talked back and forth about what I should do, because I could have talked about in some detail about my history with Stan, but he urged I talk about gravitational waves, which I'll do, but not quite in the way I would do in a regular conference. It's more as if I'm talking to Stan, and I'll tell you why or how. So first, a little bit of history, a couple pictures that I had. I talked at the retirement party for Stan here, and these three slides were from that, which I just picked out to show first the history. He was obviously, as we heard today, a leader in our field for 5 decades. And I just happen to have a picture of him with Peef, him with Leon and Boyce. And the last picture is actually in the meeting that we heard about this morning when he was leading the DOE study that was about the SSC. So that's just a little history. And I came to the retirement party, and I talked at the retirement party at that party or event, whatever you call it. At that event, Stan asked me to give what he called the after wine speech, which I did. And this is my slide from that. And I'm showing this slide to just reflect a little bit on my relationship with Stan and how I've approached this talk. I don't know, I may go back further with Stan than anyone else in the room, I'm not sure. We first met on the telephone when we were seniors in undergraduate school. And he was at Harvard, I was in Berkeley, and I had a summer job, or summer, whatever you call it, an internship or something at Hughes Research Labs in Southern California. And I was working on radar that summer. And I had a Harvard student who was also an undergraduate who was with me, and we were in an office together, Mason Watson. I don't know if anybody knows him. And we talked about then going to graduate school. And he was interested in going to Berkeley or maybe Chicago or somewhere. And I was interested in going to Berkeley. It was hard to go to Berkeley for someone who was an undergraduate in Berkeley. So I didn't know if I could go to Berkeley, but I had reasons why I wanted to. And Stan was his friend in undergraduate school. And of course, I had a couple friends too. And so we called Stan, and I talked to him on the phone. This is before we ever applied to graduate school, so a year before. And we talked about different graduate schools, what we were interested in, and so forth. That evolved into us both going to Berkeley for graduate school and renting an apartment, sight unseen. I'd never seen Stan, just talked to him on the phone, with Mason Watson, his friend, and a friend of mine, and 4 of us rented a old house in Berkeley near the campus. And that's when I started to really get to know Stan. So we became very close friends immediately. It wasn't very long before he left. He met Esther and left us, but we became friends. And that continued in a very kind of interesting relationship. We never always worked together, but we were always very close. We weren't particularly socially close. We didn't, meet all the time. But our careers went like this all the time, starting in Berkeley. So in Berkeley, as graduate students, we both decided to do experimental particle physics. Our roommates went in other ways, but we went into particle physics and up on the hill. Stan went to work with Louis Alvarez, as we've heard this morning. What we didn't hear is what he did there, which was pretty important. Basically, as a graduate student, he was certainly one of the principal people who developed the ability to study and find very short-lived, strong decaying elementary particles, which were discovered during his era there. And the idea of how you take the final state, multi-particle final state, and reconstruct, of course, it's common now, but reconstruct the masses and everything else to determine the particles and discover them. Much of that came out of the Alvarez group. Much of that built on what Stan did. And so it's no surprise that you saw the kind of letters from Alvarez that you saw this morning, even though it's not pointed to as one of his great inventions. I, on the other hand, decided I had to do something myself. And I went up to the 184-inch cyclotron and did an experiment. We both had the same dream when we graduated to get our PhD, which took about the same amount of time. We not only entered the same time, we more or less left at the same time. And that was to get an NSF fellowship to go to CERN. So we both applied. He got the NSF fellowship, I didn't. And so he went, and much of his career was built around the early time at CERN. I licked my wounds and took a default job, which was at Caltech as a postdoc, and I've been there kind of ever since. But through the years, we basically maintained a close relationship. And at the meeting, the celebration of his retirement, I pointed out, just having looked up at that time, that almost a third of my publications have been in different collaborations working with Stan. That's up to 2010. Of course, I went into a different area my last decade or so. So we worked together. We also talked a lot together through the years. And he's always been one of my best advisors, critics, all the words you want to put into somebody who actually I would share with. And so if I were to meet him today, I would tell him, he knew we discovered gravitational waves, so I'm not going to show you that. But it's more or less what I would tell him, kind of a doctor for you, if I were to talk to him today about where we think we're going and what the opportunities are in gravitational waves. So this talk's really meant to be for Stan, but I know you're the audience, so it'll be a little different than that. First thing is that we're rapidly accumulating examples of gravitational waves. Sorry, that's my phone. We're rapidly accumulating. O's stand for observational. I've changed from an experimenter that makes discoveries like particle physics to more like an astronomer who calls their runs observational runs instead. So it's observational run 1, which you see down at the bottom. This is the first 2 events that we saw. Observational run 2, we're now observational run 3, those are all completed. We're now in what we call observational run 4. And the important thing is the slopes keep changing. And the slopes keep changing because we keep improving the sensitivity of LIGO. And in detecting gravitational waves, we basically, the closer the source is, the easier it is to detect. We detect an amplitude, not a power. So as we make it a little more sensitive, we see further out, and we gain very quickly because we gain as the cube. And so improving the slopes here is improving the sensitivity incrementally by, say, factors of 2 gives us a factor of 8 in rate. At presently, we're just in the beginning of this 04 run, and we get an example of some sort of gravitational wave every couple of days. So it's pretty impressive considering 6 years ago was when we discovered gravitational waves for the first time. And so this is kind of where we are. I'll show you a few more things and then where we'd like to go as the next few years progresses. So first, everybody realizes the first gravitational waves we saw were the merger of 2 black holes. That's very fortunate as an experimentalist. And as an experimentalist, I always kind of believed in the idea that if you do an experiment, it's kind of a rule. You should have control over every variable so that you get the right answer on the experiments you do. That's not possible for us here. We needed to not do what Hertz did, which is make a source to detect electromagnetic waves, and then the rest of it followed, because we can't make a source that's strong enough to do gravitational waves, so we have to rely on nature. Luckily, nature provides not only a source, but sources that are interesting enough to be useful for doing science. So we detected in the first detections black hole mergers. That wasn't our first goal. Our first goal was neutron star mergers, not because black holes wouldn't be interesting, but because there was absolutely no way to do the prediction of what the rate would be. So we got lucky. We discovered gravitational waves from black holes. We then saw it with neutron stars, so we would have discovered it 2 years later if nature wouldn't have been so kind to us. But we discovered them. Now we have, roughly 100. And the question for the black holes for us is, what are the features? How does it fit into what we know about astronomy and cosmology? What is their origins? And and as I said, what are their features? So we're starting to measure distributions. I'm not going to show you a conclusion. We're just starting to do the kind of thing that we're used to doing in particle physics. Of course, with only 100 events, you can't do too much. But this already has the feature that you can even see here, that the different models we have compared to the data, that the data goes to much higher masses than any of the models that we compare with. This is a mystery because the naive view is that the way these black holes are made is by stellar collapse. That is, you have a heavy star and it collapses and makes a black hole. Occasionally you have binary systems, but the masses of them can't be too heavy, because stellar systems themselves can't be very heavy because they're unstable if you make them very heavy. So they're not expected to be at the masses they are. So it's already a puzzle that we see such heavy, by heavy, I don't mean like the center of the galaxy, but heavy relative to stellar black holes. And so we're pursuing basically the distributions to understand what their masses are. They're already in the region of what are called intermediate mass black holes, which people didn't know that they exist. And we will, as we improve the sensitivity within a finite time that I'll show you, be able to see these out to the edge of the universe, which is be able to tell basically whether they're primordial, whether they came in the early universe, and hopefully how. So basically that's the hope there. These events themselves are very useful for testing GR. So we basically do the test of GR. You don't know these parameters, but these are these are the parameters from using general relativity, and our data shown, which shows no deviations at this point. So knowing whether GR is right or whether it's where it's wrong requires doing more than this. You want to get into the area where the fields are very strong, which is the best possibility that there's different variants that you use instead of GR itself. But we're in a difficult situation compared to particle physics, where if you have two models, you compare which one fits best. Here we have one model, and we have to just ask whether it works well, because other theories of variance of general relativity aren't carried out to the level where we can actually compare with the data. So we're doing it in a way that is not ideal, but we look at the parameters. We look at whether there's any sign of things like, for example, in this plot, a dispersion term. Taking a limit on the dispersion term, you can ask, it physically means if they're a graviton with each gravitational wave should be just ripples in space and time itself in Einstein's theory. But we can ask logically the question of whether there's a carrier like the photon is for E and M. And in this case, we don't see any evidence by putting in a term, and we set the best limit that exists on the mass of a graviton, which you can see in this plot here. So that's test of GR that we do. Of the 100 events, we already are in the situation where we see ones we don't know what to do with yet. For example, what's known in astronomy or in life for compact objects are neutron stars. They weigh 1.4 times the mass of our sun. And then there's black holes. Black holes can't be too light or they wouldn't be black holes. To be a black hole, they have to be something like 5 solar masses. It's not clear exactly what, but something like that. And we already have examples that are in between. So maybe that's measurement errors. We only have 100 events, but we have intriguing events in the sense of maybe there's other things besides neutron stars and black holes. We also see heavy ones that, as I mentioned before, shouldn't be there by the standards of these black holes coming from the collapse of the star, because there shouldn't be that heavy of stars. This is an example of an 80, I think it's an 80 solar mass and a 60 solar mass up to 140. So it's extremely heavy, heavier than the first ones we've seen. And recently we've seen the combination black hole and neutron stars, which are interesting from the point of view of tidal effects and all kinds of things you can calculate. And we're beginning to see those. Of great interest is somehow combining information on gravity and gravitational waves with what astronomers measure. To do that, we have a challenge. And the challenge is we have to not only find gravitational wave events, but find them fast enough to tell astronomers and accurately enough so we don't scare them away by telling them we see something and then going, oops, too many times. And that turns out to be a big challenge because we're comparing with Einstein's equations and so forth and have to do this very quickly. So we have a rather vigorous effort to try to get a reliable, not 100% reliable, but reliable identification within a few minutes that we've seen gravitational waves. And then we announce it to the astronomical community. At first, it was just the astronomical community that made an agreement with us, so they were partially to blame if we withdrew. But now we're confident enough that we just announce it, and whoever wants can change and look where we look. The power of being able to do this requires being able to localize and tell telescopes where to look. We look everywhere with a LIGO, but to ask telescopes, we have to localize. To do that, you need 3 detectors. We did that by triangulation in the first event where we saw a neutron star merger. Presently, even though I showed you the optimistic 04 run, we don't have a third partner. The third partner was the one in Italy. It was always weaker than ours. They're not able to keep up, so we're much more sensitive than they are now. So they've given up and turned off, and they're trying to make it so we don't have a third detector running. We will in the future, and then we'll keep going. If nothing else, we're building one in India, which I didn't mention, as a third one, which will control ourselves. That'll be finished within about four years from now. Anyway, we want to triangulate. We did that on one event, which people have heard about. And there's an interesting, this is a picture. One part of this I'm proud of is the pointing of LIGO compared to the pointing on high energy photons was better, despite the fact that astronomers told us we would never point well enough for them to look. And so I was kind of proud of this. What's interesting on this is the gravitational wave signal is down at the bottom, the time frequency one that's kind of blue. And then I've continued the line up. And you'll see the peaks, which are the high energy gamma rays, which are seen in the Fermi satellite, other satellite. It's about 2 seconds later. You expect it to be somewhat later. Our signal comes from the neutron star itself merging. And then after it merges, there's the nuclear physics that gives out the gamma rays. So on some unknown time later, but a couple seconds. So, but within a couple seconds, we see high energy gamma rays and gravitational waves. You don't have to do any analysis. Within 2 seconds, we do know the source for this. It was looked at with astronomers. It's 150 million, I'll talk about light years, because we're not astronomers here. 150 million light years away. That's 1.5 10 to the 15 seconds. This is 1.5 seconds. So to 1 part in 10 to the 15, we know that gravitational waves go at the same speed as photons, which is a pretty impressive and simple conclusion. This whole thing was then looked at by more than 2,000 astronomical telescopes of one sort or another, all the way over days and weeks out to the radio. And then it can be compared with the light curves that astronomers use and fits very well a particular picture called a kilonova picture, which I won't do in detail. Another side thing is that gravitational waves can be used, if it isn't resolved sooner, to resolve the tension, as the astronomers call it, about the Hubble constant. I show here the two curves for the Hubble constant. If I just take this one event of neutron stars, we know how far it is away. The Hubble constant times that distance is the flow or the velocity. So you can determine the Hubble constant just from any one of these individual events. By the end of this decade, after we get back to doing neutron stars, we should have enough events to be able to, if they don't do it themselves, resolve the so-called tension in the Hubble constant. So you can see the breadth of things. Lastly, and I certainly would talk to Stan about this, is how do we improve the sensitivity and what's the long-term program? And can you pursue a long-term program? So the first thing I'll say is just looking at it from a distance, despite the fact that these are very, very tiny effects that we're measuring, we're in a very favorable position because we're limited not by physics, but by technical background. So if you go look at the Higgs boson at CERN, it's a couple % effect on a physics background. It's hard to beat that unless you go to E plus E minus or mu plus mu minus. In our case, the backgrounds are all technical. So to the extent that we can reduce the so-called noise, we gain. We also measure an amplitude instead of a power, so we gain very quickly, because if we look twice as far out, we get 8 times as many events. So we're working very hard on basically the same kind of instrument, but improving the technologies. And we know how to do that till the end of the decade, and we're more or less funded to do that through the end of the decade. And so basically this will continue on to what I show there, which is S5. We've recently also gotten to the stage where we have quantum effects that come in. And that's, for example, just thinking about it, as we increase the number of photons, that reduces what interferometer people would call shot noise and particle physicists would call photostatistics. That's what limits us at high frequencies, which is shown here. And sorry, that's for me, but at high frequencies, but at the same time as you put in more photons, you put more pressure on the mirrors, moving the mirrors, which are hanging. So basically, how do you beat that? You beat that by doing what I won't go into here, but something called squeeze light, which is a way to change the phase space so it puts less pressure on the mirror, and basically is a way to see quantum effects on a macro scale and to change the effect by changing the parameters. And that is recently put in Physics Letters just very recently. In the future, so that's kind of the near-term future. In the future, we have done almost nothing. We've just done compact binaries. There's other effects that we expect will happen. We should be able to see supernova. And seeing a supernova when the star collapses is not, we know it's not perfectly symmetrical because the final object tends to go off at an average velocity of a few hundred kilometers a second. To the extent that it isn't spherically symmetrical, it'll give a gravitational wave signal. And we can then, in the end, hope to see both the gravitational part of the collapse, the nuclear physics making neutrinos, and the light curve that to understand supernova. We just have to have a supernova close enough to do that. Gamma ray bursts fall in the same category, that it gives us a burst kind of signal. The one that I've always hoped we would do soon is pulsars. So in our own galaxy, we have many pulsars, spinning neutron stars that give electromagnetic signals that we measure in radio telescopes. To the extent that they're not perfectly spherically symmetrical, they'll give gravitational wave signals. So far, we've looked for those, but not in the optimal way. We can't do that yet. So we look for ones that are basically well known to radio telescopes, but the ones that are well known to radio telescopes are old spinning neutron stars that have settled down and probably aren't very asymmetrical. We've basically been able to limit for those well-known ones that if you think of a neutron star as being about 20 kilometers across, the asymmetry is less than a millimeter on the surface of them. Those aren't the ones you want to look at, and we're not sure without doing an independent search, which takes a lot of computing, how to do it yet. You want to see younger neutron stars, because we know that when a star collapses and makes a neutron star, the average velocity is a few hundred kilometers a second. And that means it collapses asymmetrically, and we should be able to see these effects. These are great once we can detect them, because it's more like what we're used to in other physics. It's just not something that came and you can never look at it again. Once you have a pulsar that we see, we can keep studying it for as long as we want with better and better instruments. The last source is cosmological and probably the most interesting. Not in our lifetime, Stan's lifetime, but the potential, I think, best way to get to the early universe is gravitational waves. Maybe we heard today neutrinos, but I think it's pretty hard with neutrinos. With gravitational waves, we don't know how to do it yet, but they're not absorbed. In the short term, the imprint of gravitational waves on the CMB signal is what people are looking at. But in the long term, doing gravitational waves, signals looking for gravitational waves from the early universe is, I think, the most exciting thing that you could do. Of course, we do that now, but we're in the wrong frequency band. We're at very high frequencies, and to do that may be possible, but the most likely is you want to be at lower frequencies. So the future, just very quickly. We know technically how to make the next generation detectors if we were to get funded. There's two different approaches. In the US, we talk about making just basically a bigger version of LIGO. We can do that because we know you can go to the Southwest or somewhere and do that. The fact we might even be able to pick the site where we compensate for the curvature of the Earth and not have to remove very much dirt. In Europe, they talk about going deep underground. So there's a deep, and I showed them both here. One big technical difference to make it better than what we do now, right now it's very incremental, is to go to low temperature and make the interferometer work at low temperature. That's a challenge, not fundamental, but how you pick the right material for the mirror, how you coat the mirrors and how you get the heat out without moving anything is engineering and technical problems. And we're working on that, but we don't know yet how to do it. The Japanese have tried to cool, but they did it without that research, and it's not working very well. I won't go through this. Let me just say, if you make a bigger one, the driving cost is the high vacuum system. So we happen to be working now closely, our engineers and CERN engineers, on working on all the elements that make the vacuum system expensive. And so it's a joint technical effort between us and CERN. Lastly, we're working on the optics, as I said, to move to bigger optics, better optics, and optics eventually that'll work at low temperature. So finally, basically, before we can get to the early universe directly by seeing gravitational waves from the early universe, the work on neutron star collisions gives us a piece of the same plot, if you want, of density versus temperature, which gives us the way in our labs to learn what we can about the early universe, where I show on here what you get from high energy hadron colliders, which is low density but high temperatures, what you get from, say, Brookhaven Heavy Ion Collider, and us from neutron star collisions, which in the short term is the way we're going to learn is what we can, I think, about experimentally about the early universe. Lastly, and this is the end, we want to do what was done in astronomy, which is cover all the frequencies that are possible for gravitational waves. And that's being done. I show LIGO on here, which is very high frequency. We're basically in the audio band, which is where we can work on the Earth's surface. The space experiment LISA is approved and as one of the cornerstone missions in Europe. NASA's a minor player, but it's mostly European. And they've proven already in a test flight the technology that has to be used for it. And lastly, at very much lower frequencies, some of you are aware that there was recently a paper, an announcement that they may see gravitational waves from looking simultaneously at a lot of pulsars. That gets to lower frequency. I'll remind you that this plot is exactly what's been so important in astronomy. In astronomy, in my view, as a non-astronomer, the biggest contributor to the tremendous gains of the last 50 years has been doing multi-wavelength astronomy. For 350 years after Galileo, we did astronomy, made better telescopes, but it was really starting to look at something other than a visible light that made the big difference. And so you want to do the same thing for gravitational waves. And we can see that program developing. The lowest one the low frequencies in the present scheme is by looking at known pulsars spread out over time. If a gravitational wave comes through, it changes the relative correlations between these good clocks, and you expect it to have a particular shape. So it's a noise curve, like they see. I show it next slide. This is the publication that just came out, and you can see it's not definitive, but it has the smell or the right feel of the shape that you expect the correlation to look like if there is a correlation. Of course, they're plagued by backgrounds, but right now that's the promising that they'll do that. The technologies in space look like they're in hand, so we should see multi-wavelength astronomy with gravitational waves in the not too distant future. This is just a picture of what they'll do in space. The test that they did that basically shows that they have the sensitivity versus frequency that you need to do that, and basically the scheme, which I think I'll skip. So lastly, as I said, other than the direct measurements is the polarization in the CMB experiments. We have a series of CMB experiments coming up. A big goal of those CMB experiments is to measure the polarization, the so-called B modes. That gives us basically an imprint from gravitational waves on what happened earlier, because CMB is kind of 400,000 years from the Big Bang. But if you have the polarizations there, they'll have the imprint from gravitational waves if you want translating perhaps some insights into what inflation is and so forth. So lastly, I think we can look in the long term toward a broad program that covers the large frequency range. It's on the Earth, it's in space, it's in CMB, and it should be a very rich field. So Stan was, as I said, my longtime colleague and friend. He made most of our lives much richer. This is the last picture that I showed in 2010 at his retirement event. And this one, which you've seen many times today, I chose actually to use in the CERN Courier obituary, which I wrote. Thanks.
Question for you. So in your various run periods that you showed, there is a little snippet of Kagra data, and that was without, if I saw it right, if I got it right, it was that. So that was with warm mirrors.
No, they're cold, but they basically have 100th the sensitivity we have.
Oh, because there's noise. And this is cool. The mirror are cool.
The mirrors are cool, but they're shaking too much and so forth. So they're doing it cool, but they turned off too. The Italians are not turned on, and the Japanese, they both are so far from our sensitivity that they're working on technology. And we hope
what's
they
wrong
turn
with
on.
that you said, I mean, this used to be some sense that so that you almost gave up.
That I,
No, I had the impression you've given up, but you just said, well, so that
well,
you don't
I,
have three detectors.
right now, they're not sensitive. They weren't sensitive enough to make the first detections. They were fortunately in a very advantageous position for that neutron star event, so that even though they didn't see anything, that helped us locate where it was in the sky. The trouble is this big factor that you cube the distance. So if they were twice as sensitive, they only see 1 out of 8 events we see. Right now, our sensitivity for a neutron star merger in the way we calculate it on the average in the run that's going on now is 160 megaparsec. So that's how far we see out by our way of measuring it. And when they turn themselves off, they were at 25. So it works, but 25 over 165 cubed is too small. So they basically are not participating now. They're trying to improve the technology. The Japanese experiment is even worse. They're just not there. I can't comment on their technical issues.
Will the Cosmic Explorer or the Einstein telescope be able to put a robust upper limit on a scalar component of gravitational waves?
I don't know, and I'll tell you why. In general, I mean, the problem, I showed you these graphs that were our attempt to look at Einstein's equations. And basically, all we can do now is look for deviations from that. What we need is specific predictions, whether it's scalar or anything else. We need to compare with something specific before we can.
So they won't have a common mode detection availability, right?
Right.
Back there.
So the neutrinos, have there been any coincidences between the neutrino detectors and gravity waves?
Well, we try. I mean, that's part of what we're trying to do. We have a network, and when we see something, we inform them. If they see something, they inform us. So far, there's nothing.
More questions. Okay. This question about these pulsars in our galaxy.
Mhm.
So it has to be rotating about the non-symmetric axis. That's what makes it a pulsar. And that's why it emits gravitational radiation.
It's not the axis. It's whether it's a perfect sphere or it has.
No, but but it's rotating. It's
rotating. It's
So
rotating, and that's what
rotating-
makes the electromagnetic.
Yeah, but since it comes and goes, it means it's not rotating around the symmetric axis. It's rotating around
It means it's not
the
pointing.
axis.
It means the radiation, electromagnetic radiation, isn't always pointing at us. It's
That's
a
what I'm
little
saying.
like it's.
Exactly.
Yeah.
So my question is the quadrupole pattern of the gravitational radiation
No,
it's not the same distribution as the optical?
no, it
So-
doesn't point like that anyway. It's
Exactly.
Yeah.
So what is the degree of asymmetry to which you're in the wobble, if you like, that you're sensitive to?
well, I said right now the best way I can we can talk, but the best way generally I can do is tell you it's 1 millimeter out of 12 miles. That's the diameter of a pulsar is roughly 12 miles. And right now, as I remember it, the limit is effectively, there's no deviation from a perfect sphere larger than something like a millimeter. Whether that's on the surface or somehow inside or what, it doesn't matter. There's no signal.
Lisa?
Do you think in the Cosmic Explorer era should Cosmic Explorer be able plan to do the localization on its own, or will it be able to count on Einstein telescope or other things?
Well, we're not
India.
yet funded for that.
I know.
Yeah, so the answer is we're right now in the planning, we're planning for the Einstein telescope to exist as the third arm.
One more question on millisecond pulsars. There's presumably spun up, and they don't go beyond a millisecond because of gravitational radiation. Is that correct?
Yeah,
And so you need to catch one though that's in the process of being spun up in order to have some shot at the gravitational radiation itself. Is that correct?
Well, that's not that can be true, but just a pulsar that's spinning to the extent that it has a quadrupole moment gives us a signal.
Right, but that should be much weaker than
Yeah,
the process that's spun up.
well, but maybe there's more sources around. I mean, is there really some spin up in our time while we're looking? It's true the signal would be bigger, but we can't estimate how often that's going to happen within our range. But we know there's lots of pulsars within our range. Our problem is we were very good at looking at old pulsars, not very good at looking at young ones, because we rely on electromagnetic signals.
So over at Rubin Observatory, we're excited to look for optical counterparts. But how long is 04 going to run, do you think? We're wondering if we'll start early enough to have some overlap now, as opposed to in a few years.
04 is scheduled for 18 months. We started last summer, and so it should run until the end of next year. But we may make it longer if the other detectors if Virgo turned on, actually, then we might make it longer. But the present schedule, which they were supposed to participate in, we turned on last summer, and it was going to be a year and a half.
Why wouldn't you continue?
Oh, because we have improvements to make for 05, and the gain is so fast. If we can improve this thing a factor of 2, we gain a factor of 8. So it's a different ball game. How much you want to run than particle physics, where you run and run and run to get enough statistics. Here, we want to not run so much because we have a lot of technical gains we can make to improve it and gain faster. So it's a trade-off that's different.
Are there any more questions? If not, let's thank Barry again.